Okay. The confidence interval, you're trying to locate a parameter. For a prediction interval, you're actually trying to locate a new random y of value. Okay? There's two sources of error. Okay. Prediction interval. Let y0 equal beta 0 plus beta 1 x0 plus epsilon 0. You're not trying to locate beta 0 plus beta 1 x0. You're trying to locate beta 0 plus beta 1 x0 plus epsilon 0. So that's a harder problem. Okay? Okay. Actually, I do note a typo on page 1 of these notes too. It should be if x0 is a new value of x, not xn plus 1. Right in the very first line at the bottom of the page 1, it says prediction interval. You should say if x0 is a new value of x at which we wish to predict a response y0. There's two sub-zeros that I forgot to erase. You see the n plus 1 and n plus 1, it should be y0 and x0. x0 and y0. Then y0 equals mu sub y given x0 plus epsilon 0. Okay? To establish an interval that will contain the value y0, not the mean, mu sub y given x0. All right? I'm not trying to get a confidence interval for the mean parameter, but I'm actually trying to get a confidence interval for y0. I'm trying to find an interval that will almost certainly contain y0. All right? I don't know why we are asked to do so, but let's do so. With 95% confidence, we must take account of the variability of both our estimator for this term and also the variability of epsilon 0. So how am I going to do it? I'm going to try to locate y0 by using, what's my estimator going to be? Mu sub y given x0 hat, which is simply beta 0. What else am I going to use? Well, it's beta 1 hat x0. That's going to be the center of my prediction interval. And then I'm going to use the fact that beta 0 hat and beta 1 hat x0, that depends on the n observations already made. Now I'm going to make a brand new observation. That's why I called it yn plus 1 instead of y0. But the idea is a brand new. So epsilon 0 is going to be independent of all the epsilons that went before. So epsilon 0 is independent of beta 0 hat plus beta 1 hat x. All right. This is going to be independent of anything that went before, of y1 through yn. Okay? There, okay. And so I'm going to use this as my center of a prediction interval, and I need to see how much variability is in y0 now. Okay. Excuse me, how much variability is in y0 minus mu hat sub y sub x0. How much variability is in there? What's the variance of this? Equals the variance of mu sub y given x0 minus mu hat y given x0 plus epsilon 0. I'm just plugging in what y0 is. Y0 is mu sub y, is just this mean, which is a constant. Okay? Minus this plus this. So what am I going to get? I'm getting the variance, a sum of variances. The variance, because these are independent. Okay? These are independent. The variance of a sum of independent is a sum of variances. And the variance of this first term is simply going to be the variance of mu hat, which we already worked out. So this comes out to be the variance of the mu hat y given x0 plus the variance of epsilon 0. So it's just everything I had written down plus another variance of epsilon 0, which is another sigma squared. So therefore I'm going to get sigma squared not times 1 over n plus x0 minus x bar squared over sxx, but times 1 plus that. Okay, so then I've got a wider interval, okay, by quite a bit, because I'm taking the whole variability of epsilon 0 into account. So if I want to actually figure out where a new y has got to show up on the screen, all right, then I have to take a pretty wide band, taking into account the sigma squared. If sigma squared is, oh yeah, okay, so then you get the prediction interval. So the corresponding formula shows up on that example on the computer. Comments about that? So the prediction interval is therefore the lower bound, the prediction interval bounds are therefore take the center of the interval, which is beta 0 hat plus beta 1 hat x0, and then plus or minus the sigma hat, the t nu alpha over 2, and then the square root of 1 plus 1 over n plus x naught minus x bar squared over sxx. Okay. Now, I want to switch the subjects a little bit, go back and talk about what happens. Well, somebody says, well, why do you put an intercept in the model if it doesn't seem to need one? So there's an example 2.8 in the text where the data set is shelf stocking data. The time required for a merchandiser to stock a grocery store shelf. This is page 48 of the text. Example 2.8. No-intercept versus intercept model. You have the time required for merchandisers to stock a grocery store shelf with a soft drink product, as well as the number of cases of product stocked. Well, okay, they're going to tell you how long it takes to stock X numbers of cases. 25 cases takes 10 minutes. 2 cases takes 0.28 minutes. That's interesting. Okay, this is assuming they're not going in from the truck. They're actually just stocking cases after they're already in the aisle, I presume. Okay? Okay. Because there was no lead time for the 2 cases. He did it in half a minute. Well, that's not possible if he had to, or he or she had to drag the 2 cases in from the street and so on and so forth, right? So, it all depends on the context. Here the context is the cases are already sitting there on the floor in the grocery store aisle or whatever, and then you just stock them. And this is the time. Apparently. So why, if I was stocking 0 cases, it should take 0 time. So automatically, you would think if there was going to be a linear relationship, then the line should go to the origin. And I should just be trying to find the slope. How many minutes per case? Right? 15 seconds a case, it looks like, approximately. Okay? Maybe. Just taking that one point, you know. That's a really bad estimator. But so is it reasonable to make a no-intercept model in this case? Depending on the context, yes. Perhaps. So let's do it. So what happens when we, that's a different linear model, right? And so no-intercept model for simple linear regression is yi equals, I'm just going to call it beta rather than beta 1. Beta xi plus epsilon I. Okay. So what do you think, if we go through that business, I could draw the geometrical picture again. So now, what would the least squares estimator be going to be? I want to minimize the sum of squared errors. I could maybe draw just a good old scatter diagram first. You got this business, and you're insisting now that the line passes through the origin, so it's called regression through the origin. X was positive in this shelf stocking data, the number of cases of pop, or soda pop, what have you, okay? You're going to put on the shelf. So, you want to minimize summation yi minus beta xi squared, overall beta. Slope, overall possible slopes beta. Okay, and that's the same thing as finding the orthogonal projection in Rn of the y vector onto the linear span of x. So now you have, there's no plane for the model for me, now it's just the vector x. Alright, and you've got your y in Rn, and you're projecting onto this line. Okay, and you're getting then beta hat x for the projection. Okay, that's all. Because again, this is just the square length of the difference. This is simply the square length between y and beta x. To minimize that, you're going to do, everybody has an intuition. If I want to minimize this distance between these two vectors, okay, I do the orthogonal projection, okay, under the space. All right. So maybe I didn't write it this way before, where there's a square length to the norm of the difference. So maybe that hopefully will convince you that the problem, the geometric problem, is the same. Okay. So then you do that, and so it looks like a pretty simple formula for beta. What would it be? There's just one normal equation that's going to come down, namely, I don't even have to go through the partial derivatives to figure it out. That's the convenience of this. I should have that y minus beta x is perpendicular to x, right? Y minus beta x should be perpendicular to x. So this should equal to 0. This is the normal equation. There's only one normal equation this time, because they only have to be perpendicular a line, not a plane. So they only have to be perpendicular to the one generator of the one-dimensional line. This is the residual vector, residual. Y minus beta x would be what you missed by. Okay. All right. It would be the sum. It would be the vector of all the errors. Okay, from the vertical displacements from this proposed line. Okay, and then you want to adjust beta so it's this right corresponding to getting this right angle. All right. Now, that's easy. The normal equation is, therefore, this is easy to solve. Beta hat equals summation xi yi over summation xi squared. There's no centering at the means. That's the key here in these formulas. So you sort of have an SXX prime. In other words, a different version of SXX. No centering at the mean of x, and no centering, and then and the total sum of squares also is simply going to be defined by, I put primes in my notation on the primes. This is summation yi squared because you're not centering at the mean. Okay, and this is going to be SSR prime, which is simply going to be beta hat squared times summation xi squared, similar to what we had today. We had, remember, it was beta 1 hat squared times sxx was the formula for SSR. Well, this is what comes out here. I'm not even going to go through the details. Okay? And then you have SS res prime, which is simply the difference between those two things. Okay? Which is SST prime minus SSR prime. Okay? And so you can have an analysis of variance table also. And you do. Obtain one. And maybe I'll just show the picture. Let's see. So what I did is I took this data and I put it on Excel, and the worksheet is also on. Thank you very much, Jane, for pulling that up. The worksheet is on the website again. Hopefully, if you're having trouble getting access to the website, somebody suggested in one person's case was that their computer was blocking them from an insecure site or something like that. But it seems to be okay if you do it from on campus. Okay? So maybe you should grab a couple of these files and email them to yourself or something. Okay? Remember, probably want to save it on the desktop as an actual Excel file before you attach it to your email. Okay? Unless you want to work with the web page. It's just kind of a, I don't know how that works. Don't ask me. I'm not computer literate enough to know. Okay. What kind of problems you might have. But this is the I don't know what happened here, why there's a number missing from this. I guess I have to multiply by 14. I must have killed it once upon a time. This is the, let's see. Yeah, this is the ANOVA table for the no-intercept regressional analysis. Okay? How can you tell?
It says no intercept on it.
But that I put on. Okay? I think that it doesn't do that. I put these numbers, this no-intercept and this no-intercept thing on. Excel does not do that automatically. It does?
No, it does.
It does?
Because when you do the ANOVA, you click on it and you say make the thing.
Okay, maybe it does on this one. It doesn't on this one, I don't think. But I can't remember. It doesn't say intercept included, of course, on the intercept included one. I put that one in there. So I wrote some of this stuff. I doctored it a little bit. This is not straight off Excel. Okay? Doctored it for consumption. So just be a little bit careful about that. How could you tell if you only had the ANOVA table?
Do you have both ANOVA tables?
Yeah, let's look at the other ANOVA table. You'd have to know how many observations there are. You'd have to know that there are 15 observations. Okay? So the total number of degrees of freedom is 15 when there are 15 observations. You need to know the number of observations as well. You need to know that you had 15 observations in the data set. So the total SST has n degrees of freedom. Residual has n minus 1. And there's 1 degree of freedom for beta hat. Okay? Regression. And okay. Whereas in the with intercept model, the total degrees of freedom for the total sum of squares says n minus 1 degrees of freedom. The residual sum of squares says n minus 2 degrees of freedom, 13. And the regression sum of squares says 1 degree of freedom. Okay? So those are the differences between the degrees of freedoms in the two things. Okay. Now, those are the two straight line fits. They look almost the same. The intercept is 0, of course, in the no-intercept model. And there are no t statistics. Okay? Here what you have is a t statistic for testing beta equal to 0. 91.13. We didn't talk too much about t statistics yet. What is the t-statistic? You can talk about confidence intervals for. We talked about the confidence interval for beta 0 hat plus beta 1 hat x 0. By taking x 0 equal to 0, I can certainly get a confidence interval for beta 0 hat. I can also just get a confidence interval for beta 1 hat, or for beta hat in this no-intercept case. All the normality theory, when you apply it, gives you similar results. So you just have to know what the formula for it is. What's the variance of beta hat is sigma squared over summation xi squared. This is playing the role of the SXX. Okay? So what you have is that the t-statistic, t, equals beta hat, t, if I have h naught beta equal to 0, so there's no slope, okay, so, and the line would go through the origin, okay, which takes no time at all to deliver any of these cases to the shelf. Okay, that would be kind of silly, but if I had that, then how would I test that? What I'll get is that under this hypothesis, under h naught, then t naught equals beta hat minus 0 over its standard error, which is sigma hat over the square root of summation xi squared. That's the standard error. Standard error means replace sigma by sigma hat in the formula for standard deviation. Should I say that again? SE means replace sigma by sigma hat in formula for standard deviation STDEV of beta hat equals the square root of the variance of beta hat. Okay, that's true throughout the course. Any estimator. The standard error just means the square root of the variance with sigma hat in place of sigma. Okay, so if I take t naught equals this, because under the null hypothesis beta equal to 0, so I have to subtract the mean under the null hypothesis. The mean of beta hat is beta equal to 0 under the null hypothesis. It's beta hat minus its mean over its standard error under the null hypothesis. Then this is a sample value from a student distribution. T naught is a sample value of t, in this case nu, where nu equals n minus 1 under h naught. I'm going to go over the margin. Under h naught, t naught is a sample value of t nu with nu equals n minus 1. This is a no-intercept case. In the intercept case, it's t nu where nu equals n minus 2. All right? So just the degrees of freedom changes. Yes, Shane?
So is it always going to be whatever number of observations minus...
It's the number of degrees of freedom for sigma hat is the nu. Okay. Nu equals df for sigma hat. General formula. Okay? Degrees of freedom for sigma hat. And that is shown right here. 14 in this case. All right? So, in the no-intercept model. So here he's getting the t-statistic is 91. To calculate the p-value, you compare that with a student random variable of 14 degrees of freedom. All right? Down here, you need to raise it up just a little bit. Down here, when I had the with-intercept model, the t-statistic for the slope is 49. and I have to compare that with a student random. That's still an awful big value relative to a student random variable which state values between -3 and 3. Okay, I have to compare that to a student variable that has 13 degrees of freedom. Okay, to get my p-value. These are all computed exactly, but I mean automatically by the computer, obviously. Okay, but it's known to refer to this 13 degrees of freedom for this one. Okay? You're actually getting a confidence interval for beta 1 hat and beta 0 hat in the with-intercept model. You're getting a confidence interval for beta hat in the no-intercept model. Now, how do you compare the two? Well, it looks like the intercept's kind of small, you know, in the with-intercept model. I mean, the lines look almost the same. Just visually, it looks like it's the same problem. So you want to take the one with fewer parameters. Now, that's going to be borne out by the fact that, and the author's choice between the two models is based on whether the mean square error, or the residual, in other words, whether sigma hat squared is smaller in the no-intercept model. If the sigma hat squared is smaller, or sigma hat is smaller in the no-intercept model, then you choose the no-intercept model. What is sigma hat? Mean square for error is 0.089. That's the sigma hat squared. 0.089 in that model is 0.093 here. So there's a slight savings. Basically, you save a degree of freedom. You get to divide by 14 instead of 13. But the residual sum of squares is almost the same because the intercept is almost 0. So the residual sum of squares is almost the same because you're dividing by the one more degree of freedom. Mean square for error is smaller. Okay, and so he says, okay, in that case, that's kind of the decision. We'll say, take the no-intercept model. Just if sigma hat squared is smaller. Yes?
And is that also the reason why the bounds on beta 1 are slightly smaller in the no-intercept model?
Bounds on beta 1? Yes. The width of the confidence interval is smaller. Okay. Even though the T13 percentage points will be T14. No, yeah, the T14 percentage points are also even smaller. Okay. You're saving a degree of freedom because you're not throwing extra parameters into the model. So you're saving on your, you only had 15 data points. Okay. If you had 150 data points, it might have been the with-intercept model that would have won the day. Okay. Comments or questions? More comments or questions? Okay. All right. We're almost done with chapter 2. There's some theory at the end, though. Okay. So grab this if you want to. I mean, there's nothing to do there. It's just on the regression. I guess maybe I should just point out that on this, put the picture on one last time. Try to freak out your camera, Nick. How do I do the no regression option? I mean, the no intercept option. Under Tools, data analysis is there now on this machine. Okay, because remember we did the add-ins. Okay, then if I want, I go again to regression, and I put the input range and input x range and all that's the same, and then constant is 0. That's the key. I plug that in. Okay. Maybe I should just do it again to make sure the no-intercept shows up there. Let's go ahead. Cases was X. Y. No, time was Y. Right here it was time. That was the Y, and the input X range was here. We'll get a new worksheet just to see how this is working. All right. Constant is 0. Output range. New worksheet. Okay. And I'll just go ahead and say OK to that. Let's see. There it is. Summary output. See, it doesn't say no intercept. It would be nice if it did. But you can tell because, again, it's 15 observations and 15 total degrees of freedom. All right. Now we can quit. I just wanted to check, because I would like to say no-intercept too. Now I'm going to say a few things, and then we're going to go on to the beginning of Chapter 3, I think. Just go ahead and say how we're going to generalize simple linear regression. There are a few things to say that are theory. Quite a bit of theory. Okay. At the end there in section 2.9 and 2.10. They're going to go over a lot of theory, and they're not going to really prove much of it. But since in Chapter 3 they're going to talk about maximum likelihood estimation again, I thought just for your education you should see what a maximum likelihood estimation is. You'll see it in some other statistics course too. But then I'll get it out of my system, and I won't have to cover that again in Chapter 3. So I want to skip as much of the recomputation as possible in Chapter 3 by doing Chapter 2 well. That's my method. Because it starts to get more abstract looking with matrices flying around and so on. And if you don't see how it works in Chapter 2, then you tend to get lost. So first, there's this theorem called the Gauss-Markov theorem that we'll just write down. And it's proved in an appendix in the general case of multiple regressors. And I guess this is on the top of page 4 of these notes. The Gauss-Markov theorem this is for simple linear. I'm only going to state it here for simple linear regression, but it's going to be generalized in that appendix. Beta 0 hat and beta 1 hat are the best linear unbiased estimators for beta 0 and beta 1. Linear unbiased estimators. For beta 0 and beta 1. Sometimes this is abbreviated by saying the beta 0 hat and beta 1 hat are blues. B-L-U-E. What does the word best mean?
The variance is small.
Variance as small as possible. Okay? Linear, we already saw that there are linear functions of y's. Summation CIYI. Okay? Unbiased means E beta hat equals beta. Okay? Estimators. Okay? That just means that they're random variables constructed from the data y1 through yn. Some function of the data y1 through yn. So among all possible linear and unbiased estimators of beta 0 and beta 1, I could construct some other ones. These aren't the only linear and unbiased estimators of those. You might say, well, where would you get another one? Well, okay, we could make sort of one up ad hoc. But among all of them, these have the smallest variance. So they're the best in that sense. Smallest variance would be a natural criterion since they're already unbiased. A natural criterion for goodness is you take the expectation of the square of the distance between the estimator and the thing you're estimating. Okay? So the mean, normally what you do is you look at the mean square error in the sense of expectation of if you have an estimator theta hat that's estimating theta, you look at this thing and you square the distance. Okay, and then take the expectation. That's the, and normally you're trying to minimize that. If they're already unbiased, and then this comes out to be remember the expectation of a square is the variance plus the square of the expectation. Well, the square of the expectation would actually be the bias. Again, using the expectation of the square of a random variable is the variance plus the square of the mean. So, and I don't have to put theta hat minus theta in the variance because theta is the constant. Okay, so theta is the parameter, theta hat is the estimator. This is the usual criterion to make this as small as possible. Make this. Now, you can still have a non-zero bias. You can have an estimator whose variance is small and still have non-zero bias. That could be better than an estimator that has zero bias and a larger variance. That is possible, and that's going to happen actually in some cases. But anyway, we're only considering among the class of unbiased estimators. Among the class of unbiased estimators, so bias is equal to 0. And of course the variance is the criterion that I want to minimize the variance if the bias is 0. Okay, minimize mean square error, minimize the variance. All right, so that's a theorem called the Gauss-Markov theorem. Now, if in addition we assume that the epsilon I are normal, this is no normality assumption required. Here. All right. But now if in addition we do assume the epsilon I are NID, zero sigma squared, then I can actually write down the joint distribution of the yi's. Again, we're going to assume that x1 through xn are fixed. We're still working with that. And I can actually write it down and get the joint density of the yi's. It'll be a jointly normal density. I mean, it's just going to be a product of things. So then, you can talk about the likelihood function, the joint density, f of y1 through yn. Okay, L for likelihood. It just means the joint density. That's going to be 1 over the square root of 2 pi sigma to the nth e to the minus 1/2 is going to be a product. I goes from 1 to n. There's this 1 over square root of 2 pi sigma from each of the normal densities. There's going to be a product of n normal densities. yi minus beta 0 plus beta 1 xi squared over 2 over sigma squared. Like that. I put the minus 1/2 up in the front in the exponent. Okay? That's the joint likelihood. And there's another general formula for finding estimators, and that is to take the maximum likelihood estimator. You maximize the likelihood for fixed data, y1 through yn. x1 through xn are already fixed constants. But now I fix y1 through yn, fix the data, the column of y, and try to find the beta 0, beta 1, and sigma, 3 things simultaneously that maximize this likelihood. And that can actually be found. Okay, L is maximized, the maximum likelihood estimates. If you go on in statistics, you'll be studying the maximum likelihood theory. And sigma. Okay. So what do I do? Okay, L is some likelihood is actually positive for all y1 through yn in Rn. y1 through yn in Rn. And it'll be maximized precisely if the natural log is maximized, because the natural log is an increasing function. So this is maximized. L is maximized for fixed y1 through yn and x1 through xn, already fixed, when log L is maximized. I'm maximizing in the parameters. Saying it's an interesting principle. You're trying to figure the values of the parameters that would have made the data the most likely. Would have made that particular set of data the most likely. It's a cute criterion. Anyway, it works very powerfully. So you can actually just do that, and you get a bunch of equations. What does it look like? If you take the log, then the log of L comes out to be, let's see, what does it come out to be? Minus 1/2 minus n over 2 log 2 pi. That's just a constant. Minus n log sigma minus 1/2 yi minus beta 0 plus beta 1 xi squared over sigma squared, like that.
You have to do the sum in there somewhere though, right?
Sum. Yeah, because there was a product, so there's a sum now. I hope I made that in my... I missed it in my notes. There's a summation symbol that's missing. Twice. 3 times. 4 times. On the bottom of page 4 to the top of page 5, put in 4 summation signs. Okay. I finally got the summation signs when I wrote down the equations. Okay. So every time you see the yi minus this, there's 4 summation signs. Okay. So now, then you go ahead and take the derivatives. What happens when I take the derivatives with respect to beta 0 and beta 1? I get almost exactly the same normal equations I had before. It's just this divided by sigma squared. Sigma squared, when I take the partial derivative with respect to beta 0 and beta 1, I am going to go back to partial derivatives now. The sigma squared will just sit down here in the bottom. Remember, this is what I wanted to... when I take the partial derivative with respect to beta 0 and beta 1, this goes off. And I just have this. So I just get my normal equations that I had before. So partial with respect to beta 0 log L equal to 0, and partial with respect to beta 1 log L equal to 0 gives me the same things I had before. It gives me that beta 0 hat times n plus beta 1 hat times summation xi equals summation yi, and it gives me beta 0 hat times summation xi plus beta 1 hat times summation xi squared is equal to summation xi yi. Gives me this before. The sigma squared in the denominator is there, but since I'm setting equal to 0, it scales out. Then I have one more equation, d by d sigma log L equal to 0. What does that give me? I get a minus n over sigma. And let's see, I'm going to get a minus sign here, but I'm also going to get a minus sign from the derivative of sigma to the minus 2. Sigma to the minus 2 differentiates to minus 2 sigma to the minus 3. The minus 2 will cancel the minus 1/2. And I get plus summation yi minus beta 0 plus beta 1 xi squared over sigma cubed equal to 0. So that gives me sigma squared equals the sum of squared errors divided by n. Not by n minus 2, but by n. So that gives me, I should put, since the maximum likelihood estimators, and they're potentially different than before, actually, I put a tilde on here. Sorry, not the hat. Even though the tilde, beta 0 tilde equals beta 0 hat, beta 1 tilde equals beta 1 hat. And then I get a sigma tilde. Sigma tilde squared is equal to summation yi minus beta 0 tilde plus beta 1 tilde xi squared over n. I goes from 1 to n. So beta tilde versus, and there was a typo in the book actually, sigma hat squared is equal to, therefore sigma hat squared is n over n minus 2 sigma tilde squared. Because remember, I divide by n minus 2 to get the sigma hat squared. I take because beta 0 tilde is equal to beta 0 hat. So this is really the residual sum of squares here in the numerator. And then divide by n. The n is not under the square sign. So there's a typo top of page 52 where it's relating the sigma hat squared to the sigma tilde squared. He says there's an n over n minus 1 relationship. It's actually an n over n minus 2 factor. The reason where he's getting the n minus 1 is that if you if it's just a model with only beta 0 in there, okay, which is what you do the first course in statistics, you get the n minus 1 over the n. And no beta 1. If beta 1 is equal to 0, there's only one parameter, then the sigma tilde comes out to be, well, then the sigma hat squared in least squares comes out to be, have n minus 1 degrees of freedom. Okay? So if beta 1 is 0, the sigma hat squared will come out with an n minus 1. That's just ordinary statistics. Remember it's the sample variance. Sample variance. So this is on the aside over here. If yi equals beta 0 plus epsilon I, what's the least squares estimator for beta 0? Beta 0 hat equals y bar, and then SS res simply is summation yi minus y bar squared. Okay? And sigma hat squared would therefore be summation yi minus y bar squared over n minus 1. That'll be unbiased for sigma squared. Okay? So that's why he got the mistake on page 52, because he's thinking about the way he teaches statistics. Okay, to get this. There's a maximum likelihood estimation. If you go to the maximum likelihood estimation on the normality assumption, you get sigma tilde squared, again, equal to summation yi minus y bar squared over n. The other version of the sample variance. So maximum likelihood estimator gives the sort of the more natural version of the sample variance for the estimator of sigma squared. Okay. Well, there you have it. It turns out, and I go through the computation, that under the normality assumption, in fact, the mean square error of sigma tilde squared is less than the mean square error of sigma hat squared. It's actually a better estimator than sigma hat squared under the normality assumption. It has a smaller mean square error. Its bias is non-zero. But you can go see the notes. The variance is also smaller. Because I'm dividing by more, the variance is smaller. Okay?
The bias is asymptotically 0.
Asymptotically 0, but when you add them up, you actually get something which is smaller in variance than the variance of sigma hat squared. You have to use the variance of a chi-square, random variable, and all that, so I don't want to go into this here. The variance of a chi-square of nu degrees of freedom is 2 nu. If you want to go through the calculation yourself. Okay? All right. It's not a much smaller variance, but it's smaller. Okay. So the theory is that under this, since the least squares estimators coincide with the maximum likelihood estimators, they have minimum variance among all unbiased estimators. So beta 0 hat and beta hat not only the best linear unbiased estimators, they're actually the best unbiased estimators under the normality assumption. Okay. So this is kind of a cute thing to try to organize the theory by stating these facts. Okay. Now, then there's the case, one last case, section 210. Maybe I'll skip that for today. And that has to do with when xi and yi are now both random variables. And you assume that the pair xi, yi is jointly normal. How many people have seen bivariate normal distribution? 2 out of 6. Okay? So that's not many people. That's why I thought I'd skip it, because it's a very hairy calculation.
So then will you mind telling us that on the last problem of the homework that's due tomorrow, that just treat it like any other problem, because it is a
Let's see.
It is one that...
213, it has something to do with bivariate normal? Yikes. Maybe I better cover it. I have 10 minutes. Okay.
I think you should just say you treat it like any other scenario.
Okay. Here's the deal with 213. Let me give you the hint. It says, update on ozone trends.
Oh, that's not. Never mind. It's the one that's due next week.
Okay.
It's the weight versus part stuff. It's the first assignment. Yeah, 210.
210. So it's the Monday's assignment. Okay. Yeah. I think maybe you should read these notes a little bit, what I wrote here on pages 5 and 6 of my, bottom of page 5, page 6 of my notes, and together with the text, which it matches, only I've got a little bit different way of displaying it, and we'll come back and talk a little bit about that next time. I want to summarize what we've done in Chapter 2, all except for that one topic. So what he's going to do in section 210 is say, okay, now pretend x is also a random variable. So you have the pairs xi, yi. And now all our interpretations under that case will be for repeated sampling of pairs, not for repeated sampling of y's given the x is fixed. Okay. Nothing much changes. The t-statistics and all that stuff stay the same, but we have to assume more. We have to assume that xi and yi are jointly normal, essentially. We don't have to, because he says I can assume just a slightly less than that, but in practice, that's what we have to assume. So it's again covering, giving some more theory to discuss the assumptions you're making for the regression. Okay, so why don't we have a little look at that yourselves and just stare at it for 5 minutes before you have to look at the onslaught of notation. Okay? See if you can understand what they're talking about. And so then what I would like to say is, in the last remaining 2 minutes, is the matrix formulation of simple linear regression. And then that's where we're going to start with Chapter 3 when we start, after the slight discussion about this stuff at the end of Chapter 2, and then we'll start with Chapter 3. So what is the matrix formulation? And then I'll have to finish that up tomorrow anyway. Let me just say a couple things to maybe whet your appetite and maybe look at the beginning of Chapter 3 too. Does everybody get the syllabus now? All the problems are out there? The matrix formalism, what I do is I introduce a matrix X equals the first column is just that one, the vector 1, and the second column is just the vector X. So matrices are just a nice way of writing things down more compactly. But of course I'm going to display them uncompactly here to say what it is. We have to get this in our mind. And then I'm going to take beta. This is an n by 2 matrix, and I'm going to take beta as a 2 by 1 vector, beta 0, beta 1. So now I'm not going to, I think they put a bold sign on the beta in the book, or maybe they don't. I can't remember. Yes, they do. It's bold. So I could underline it if I needed to. How would I do it?
Put a vector mark over it. Now a vector.
Well, you could do that, I guess. I probably don't most of the time, because it's understood what beta is. It's the vector of parameters. Okay, from now on, it's not going to be a scalar. It's going to be a vector of parameters. Unfortunately. Okay. The thing with the subscripts are going to be the parameters. I know I used beta as a scalar in the no-intercept model, but that was an anomaly because we're going to barely ever discuss the no-intercept model. Okay. So I'm going to have this, and then I'm going to have y. That's also bold. It's going to be y1 through yn. It's be bold in the book. I'll put an arrow over it. There's going to be, and then it's epsilon. It's going to be just simply epsilon 1 through epsilon n. Okay. So now I can write the equations yi equals beta 0 plus beta 1 xi plus epsilon I goes from 1 to n. Simply rewrite that. That's n equations, right? I can write it as one vector equation. Because remember, two vectors are equal if and only if the corresponding components are equal. That is, if and only if the difference is the 0 vector, 0, 0, 0, 0, 0. So this can be written as y equals, let's see, maybe I should write this, y equals, let's put it in the intermediary stage, beta 0 times 1 plus beta 1 times x plus epsilon. Okay, that's the intermediate stage. That's one vector equation. If and only if y equals x beta. Okay, plus e. There's the shorthand version. Okay, because remember, when I multiply x times beta from linear algebra, we're going to have to remember a little bit of linear algebra now. This simply is beta 0 times the first column of the matrix plus beta 1 times the second column of the matrix. That's how matrix multiplication is defined. Okay? The set of all x betas is simply the plane that I had. Right? So the linear span of 1 and x in Rn is simply the set of all products x beta, as beta ranges in R2. Okay? Okay? So that's another way to write that plane. Okay? So that's the matrix formulation. Y hat is simply going to be x beta hat whenever I find beta hat. Well, this is now a bold beta hat. Okay? So now then I do really start putting the arrow on there. Okay? That's the vector, n by 1, n by 2, and this is a 2 by 1. Okay, the vector of estimates. Okay? And all that good stuff. So we're going to start using this. So he's using, because he can't put arrows forever, it's going to be bold. I don't know. I mean, because everything is going to be bolded. Practically. There's no point for me to make a special notation for the blackboard, I think. What I'll do is, to emphasize, I'll put in these dimensions. Okay? And that'll help you at first. Comments about this? So that's how it's going to go, and then what we're going to do is actually we'll actually come up with a formula now in terms of this matrix X for the projection onto this model for means, what I'm calling the model for means, the plane, okay, which will become a little bit hard dimensional if I'm putting another column. All I'm going to do next is I'm going to put in another regressor. I'm going to say there's not only the number of cases to put on the shelf, but also, some other variable to determine how long it's going to be. The height of the shelf or something. I don't know. That's maybe not the greatest example, the shelf stocking data, but more than one column of x is more than one x variable. Okay, so that's what we'll do. We'll just add in more columns. And then everything else is going to be the same, all the same formulas. All right. So tomorrow we'll forge ahead, Chapter 3. Bring more questions. Read up these problems you're going to have for the rest of Chapter 2, because tomorrow will be the only day I'll have in class to answer questions about the homework that's due on Monday. I know it's bad. You've got to get your homework done, and then you've got to do the next set. Start looking at the next set too. Okay. Thank you.